I love monitors. I love working on monitors. I think monitors are really fantastic to work on. I mean, I've worked on lots of stuff, and I know how to do lots of technical kind of stuff, but of all the things that I repair, I really like monitors the most, really. And I like monitors for a couple of reasons. Number one, it's just absolutely fascinating how a monitor works. The way a monitor actually works is really, really interesting. And of course, that's what we're going to go over this morning. But the other reason I really like working on monitors is that I can really produce on monitors. That is to say, it would not be unusual for me to be able to fix 6 or 8 monitors in a day. It typically takes about 40 minutes, maybe even an hour, to fix a monitor. Now, that's not to say there aren't challenging monitors. There are. And I kind of like those. I mean, those are pretty cool. But most of them are pretty straightforward, and you see the same kind of maybe half a dozen, 8 problems, maybe even a dozen problems over and over and over and over again in monitors. One of the things that I do in addition to TechFest is I do a 2-week class, a 2-week, for want of a better term, a casino school class. And during that class, the main goal of the class really is monitor repair. That's really where I think most casinos should be. All casinos really can be totally self-sufficient in monitor repair. And in that class, I invite the students to bring in bad monitors. We just did one at Chip Inn's Island Resort in Harris, Michigan, which is in the upper PI of Michigan. And we had 15 people in the class, and everybody brought a bunch of monitors, and we must, in the 2 days of our hands-on lab, we must have fixed 25 or 30 monitors easy during that time period. And I didn't fix them, the students fixed them left and right, because it's really, really straightforward, real easy to do monitor repair. So the other reason I like monitor repair is that it's real easy for me to get a bunch of monitors working in a short period of time. You know, there are challenging monitors as well, but by and large, they're pretty straightforward. Now, the monitors that we use in slot machines are technically known as raster scan monitors. It's called a raster scan monitor for reasons that I'll explain later on as we go through the class. Your home TV is also a raster scan monitor. Your computer monitor at home is a raster scan monitor. Virtually every monitor that you will work on in your normal life as a technician is a raster scan monitor. There is another type of monitor that exists. It's known as a vector scan monitor. Typically those are used in military applications, air traffic control displays and stuff like that. But everything we use is what we call a raster scan. And again, I'll explain why that is later on. But a slot monitor like this one is really basically the same as your home TV. The only real difference is that there is no tuner in a slot monitor. That is to say, you can't hook up a cable or an antenna and get programming. What that means, though, is that in a slot monitor, you don't have all the complex circuitry needed to do that. The circuitry that's required to hook up an antenna is what's known as radio frequency or RF circuitry. And boy, that stuff's really hard to work on. The parts are real itty-bitty, and even the parts placement is critical. You can have a coil mounted like this, and it works perfectly okay, but if it's bent over like that, it doesn't work properly. It requires specialized equipment, a lot of specialized knowledge, and in fact, RF stuff is so hard to work on that typically, if you were to have a tuner problem on a regular home television, even a TV repairman wouldn't repair that. It's a module. He'd pop out the module and stick in a new tuner module. He wouldn't actually work on the RF stuff. But we don't have any of that in this. Also, in a home TV, there's some fairly complex color decoding circuitry. It's called chroma demodulation. Ooh, ah, ooh. And chroma means color. Anyway, that's also fairly complex circuitry. In a regular standard television signal, which is known as NTSC, and we'll be talking about NTSC later on. It happens to stand for National Television Standards Committee, NTSC. It's the standard for video that we use in the United States. In a standard NTSC signal, the black and white signal is actually broadcast at a different time than the color. It's kind of like a coloring book where it has a black and white outline and you fill it in with color. There's a black and white signal, they call it luminance, and then later on there's a chrominance or chroma color thing, and there's a complex circuit in there that kind of combines the two and lays one on top of another. We also don't have that in a slot monitor. What's left in a slot machine monitor is all of the easiest things in a television to fix. That's what we're left with in a monitor, which is a good thing. The flip side of that is, unfortunately, that it happens to be all the stuff that fails the most. Those circuits that I mentioned, the tuner and the chroma circuits that are in a regular television, they don't fail very often. The stuff that's left in a slot monitor is typically all the stuff that works the hardest, and it's the stuff that fails the most. We'll be going over this again and again as we go through this in the next 3 days. It's something you should know as a technician. The things that work the hardest are the things that fail the mostest, really, in general. So as you'll see, and just relax, I'm going to go over this a bunch of times, just relax, relax, relax. But as you go through this, you'll see that the things that fail are things like outputs, things that drive the outside world, things called output transistors or integrated circuits that are output devices. Those are the things that fail the most. There's lots of stuff in the monitor that you'll never see fail. And you just don't even have to worry about it. There's lots of stuff in the monitor that even if you didn't know if you didn't even know that it existed, you'd still be able to repair monitors because it just doesn't ever fail. So, we'll talk about all that as we go through this. Let's start off by taking a look at the picture tube itself. Oops, I don't want to make that brown. Something like a picture tube. Down here in the neck of the picture tube, there's something that's drawn on the schematic diagram like this. Like 3 backward L-shaped kind of things like that. And this is something which we refer to as the electron gun. It's called the electron gun. Here's an electron gun right here. Anyway, this is the electron gun. Now, as the name implies, the electron gun shoots out electrons, and they come out here. Well, if you think about it, it's a gun. A gun's got a barrel in it, and there's a hole in the end of the barrel to let the bullet out, and so there are the holes. This is actually technically known as an electron gun assembly. Inside this electron gun, there are actually 3 electron guns in there, and so that's why you see the 3 holes there. The electron gun. Now, in fact, this is really known as the electron gun assembly because of those 3 electron guns that are in there. Now, I have to take just a moment to remind you what an electron is. I know that we've all been through junior high school or wherever it is that you learn about atomic theory, but I just want to remind you just a little bit about what an electron is because we're going to be dealing with electrons as we go through this discussion of monitors. If you remember from junior high school or whenever it is that we learn this stuff, we know that the smallest bit of any element is known as an atom, and if you remember how an atom is built, in the center of the atom, there's something known as the nucleus of the atom. Doesn't like that, does it? In the center of the atom, there's something known as the nucleus of the atom. N-U-C-L-E-U-S, the nucleus of the atom. And then in orbit around the nucleus, there's 1 or more little subatomic particles referred to as electrons. Well, the electron is kind of like a little planet that's orbiting around the sun. Well, you know that how, like in the solar system, how we have the sun that's in the center of the solar system and all the planets orbit around the sun. Well, in a way, it's kind of the same, and in a way, it's kind of different. In the solar system, all the planets orbit in what's known as a planar orbit. They're all orbiting in what's known as the plane of the ecliptic, kind of like the rings of Saturn are all in one ring plane like this. If we could somehow look at this electron orbit, it looks different. It's all frenzied. It kind of goes all around like this, kind of like imagine a ball of yarn and seeing the final trajectory of the string as it winds around the ball. That's what that orbit would look like. And in fact, if you could see it, which you cannot, it would look like a thin shell, kind of like a thin candy shell on the outside of the nucleus. And in fact, that's what they refer this refer to this as the electron shell. They call this the electron shell. Well, the point that I'm making here is this, that we know that in the solar system we have this thing called gravity, and it's gravity that keeps the planets in orbit around the sun. In the solar system, in the atom, we have a similar kind of a force that keeps the electron in orbit around the nucleus. But we don't call it gravity. It's something else. It's something that we refer to as an electrostatic force. Just relax. You don't really have to know this. I'll get to the point in just a second. It's called an electrostatic force. It's some kind of a weird force. It's kind of like gravity. It isn't gravity. It's a lot stronger than gravity. Look, I'm barely a high school graduate. I'm not a physicist, so I don't know a lot about it. I don't care. It doesn't help me fix anything to know it. But it's this electrostatic force that keeps the electron in orbit around the nucleus and kind of keeps it from flying off into space. Now, the way this works is that the electron and the nucleus have two different polarities, two different charges, as we call them. Here in the center, the nucleus has what we refer to as a positive charge. And the electron in orbit around it has the opposite charge. It has a negative charge, and opposite charges attract is really the point that I'm getting to here. You know how, like, if you put two poles of a magnet together, if you put, like, the north pole of a magnet next to the south pole of a magnet, how they attract each other? Same exact thing. Opposite poles of a magnet, north and south pole, attract. Same thing here. Opposite charges attract, and that attraction is what keeps the electron in orbit around this centrally located nucleus. Everybody with me so far? Well, the point that I'm making here is this. Two things. Number one, opposite charges attract each other. And the other half of that, and you can kind of guess where I'm going with this, is that if I try to put two of the same pole together, they'll repel each other, won't they? If I try to put two south poles or two north poles together of a magnet, those guys will repel each other. Same thing with electric charges. If I put a positive charge near a negative charge, those things will attract each other. If I try to put two negatively charged, let's say two negatively charged electrons near each other, those guys will repel away from each other. Is everybody good on that? That's kind of a pretty basic understanding. So, number one, opposite charges attract, like charges repel. Number two, and this is probably the most important thing, and this is really, really kind of where I'm going with this, an electron is a real thing. It's a real physical particle. My point is, it's not an imaginary thing. I think of an electron as like a BB, like a little sphere or a little BB, a little ball with a negative charge. Now, it may or may not be that. There's some superstring theories that say that, oh, an electron is a vibrating string or something like that. We're just technicians. We don't care about that. But it is important to realize that it is a real thing. It has mass. It is a certain size. It has a certain weight. It occupies space. It's a real, honest-to-goodness thing. And, of course, that's what's actually shooting out of the electron gun itself. That's what's coming out of the holes in the electron gun is these electrons. Everybody cool on that? Okay? Everybody can shut off their cell phones now, okay? Including me, I suppose. I probably better do that. Hang on a sec. Let's do that. Let's all shut off our cell phones, shall we? Okay. Now, coating the inside of the glass front of the picture tube there's a substance known as phosphor, P-H-O-S-P-H-O-R. Not phosphorus. Phosphorus is what they make match heads out of and stuff like that, but something known as phosphors. And there are actually three different colors of, whoops, go back over there. There are actually three different colors of phosphor, and they're laid down in stripes or dots down in front of the screen. In some cases, they're dots. In some cases, they're stripes. I'll show them to you in just a second. There's a stripe of red phosphor. Right next to that, there's a stripe of green phosphor. And right next to that, there's a stripe of blue phosphor. And then this is repeated across the face of the picture tube, red, green, and blue. And of course, they're much more closely spaced than I'm drawing them here on the board. Red, green, and blue are the three primary colors of light. By combining red, green, and blue, we can make any color that we want. For example, if we were to mix red and blue together make a color known as magenta. I'll show you these in just a second. Blue and green mixed together make a kind of a light blue-green color known as cyan. And believe it or not, red and green mixed together make yellow. And that's what you see here on the front of the screen. Now, you'll notice that there's the display that you see on the video is a little bit different than what you're really seeing here in the class. And that's because of the difference in the scanning rate between what the camera is doing and what the monitor is doing. But what you're seeing here is this. For example, this color is blue, obviously. This is red. This is magenta. This kind of purple color that you see here is magenta. Here's green. This is cyan, C-Y-A-N, cyan, not cayenne like cayenne pepper, but cyan. And this is yellow here. Yellow is red and green mixed together, and that's white. And of course, these are the three primary colors. So if I combine all three primary colors, of course, that makes white, doesn't it? Where all the colors are off, that's black. Where they're all on, it's white. But I can kind of show you this up close and personal here. Let me switch to the close-up camera. All right, so what you're seeing here is this. Here's black. Here's where all the phosphor dots are off. You really can't see them. Let's move over to the blue phosphor. Now, remember, we have a little deal going here with the, there you go. So that's just the blue phosphor. Now, the colors do look a little odd compared to what we're really seeing here because the camera picks it up in an odd way. Here's the boundary between the red phosphor and the blue phosphor. Now we're going to come up with magenta. And it's fairly difficult to see, but if you look real carefully, you can see the red phosphors and the blue phosphors are both lit up. Now we're going to come up to green. Here's the boundary between magenta and green. So there's the green phosphor, just the green phosphor. Now we're going to come up to cyan. And cyan is green and blue mixed together. And now we're going to come up with yellow, which is really kind of surprising that it is actually the red and the green phosphors both illuminated at the same time. And that makes yellow. And then finally all three are on, and that makes white. We are not just limited to those, what we call the primary and secondary colors here. By combining red, green, and blue in different combinations, we can make any color we want. We can make flesh tones. You can make like any color. Your regular home TV works in exactly the same way. And in fact, if you have a computer at home, you probably have some kind of a paint shop program. And as you know, you can vary the palette between 100% and 0% of any color that you want, red, green, and blue. So by doing that, you can actually make 24 million different colors. Not that you can actually perceive 24 million different colors. You can't really, but it's possible to make them. And so this works in exactly the same way. So each of those guns is precisely aligned so that its electrons only strike one color phosphor. So, for example, we have the red gun. Well, we have a gun whose electrons only strike the red color phosphor. Amazingly enough, we call it the red gun. And we have a green gun, and we have a blue gun. Whoops. Well, somewhere we have a blue gun. And by combining all three together, you can make the color bars. And like I said, you can make any color that you want. You're not just limited to those things. Now, in order to make the electron gun emit those electrons, it actually does have to be, it does have to be heated up somewhat. In order to get that thing to emit the electrons, it does have to be heated up. And so down in the neck of the picture tube, You know how sometimes you can look down in the neck of the picture tube and you can see the kind of an orange glow? Sometimes, not always. What you're seeing there is the heater. Let's go back to the picture tube itself. Oops, come on. Right there. So here's the picture tube, and I already showed you these three backward L-shaped things here that are actually part of the electron gun assembly. They're not the whole electron gun assembly, they're only part of it. These are referred to as the cathodes. These are called the cathodes. The part that actually emits the electrons in the electron gun is called the cathode. Now, what the cathode really looks like on the electron gun is a cylinder like this. It's just a little cylinder like this, and coating the top of the cylinder, there's an element that's painted on the top of the cylinder, and it's known as barium. B-A-R-I-U-M. Barium is one of the elements. And it's actually the barium itself that is the source of electrons. Believe it or not, when you first get a new picture tube, there is actually a finite amount of barium that's in that picture tube. Eventually, that does get used up. Eventually, that barium will get stripped away, and when it does, that gun goes completely dead, and you can either lose red, green, or blue, depending on which gun is dead. And of course, we'll talk about this as we go through the program later on. But it's the barium itself that is the source of electrons. And you've all seen monitors that have been on the floor for quite a while, and they get dimmer off and dimmer and dimmer and dimmer. And that's because the barium is either wearing out or somehow becoming contaminated. Later on in the class, if you go to the Sencor seminar, you'll see where they have a really cool piece of test equipment that can actually kind of recondition the electron gun in some cases when the barium becomes contaminated. And you'll see that if you attend the Sencor seminar. But that barium does have to be heated up. And so down in the neck of the picture tube, there's something that's drawn on the schematic diagram like this. Three little points. Like this. Let me just kind of zoom in on it. These three little points, it'll either be drawn like this, or in some cases you will see one point like this. One thing that looks like that, and then the three cathodes are drawn like the three backward L's like that. But this is what it looks like on the schematic diagram. What it really looks like is this thing up here that I just showed you right up here. This thing right here. The heater actually goes up inside this thing. The part that you see glowing is this little part sticking out here, but the majority of the heater actually goes up inside this cathode. It doesn't touch the cathode, it just kind of sits inside there and heats up that barium, and that's what releases the electrons. In order to get the electrons to come off of the barium, it does have to be heated up. This is a really important thing to know. That CRT heater, which is only designed to work off of 6.3 volts, it doesn't matter whether it's AC or DC, it doesn't matter, just 6.3 volts, so it isn't very much voltage, heats up that barium, and that's what releases the electrons. It's important to know that the cathode, which is what I'm showing you here, does not shoot out the electrons. The cathode simply releases a cloud of electrons. There are other elements inside the electron gun that we'll take a look at later on that pick up those electrons and shoot them out toward the front of the screen. The cathode is heated up and it just kind of lets the electrons out. Let's take a closer look at the cathode so you can kind of see what it is that I'm talking about here. So here's the electron gun, and boy, you can really clearly see it here. This cylinder is the cathode. This cylinder part that you see right here, this is the cathode. And you see these two little wires, and they look a little white. See, I'm just touching one here. These are the two heater wires. These heater wires go up inside this cathode. So the electrons come off the cathode. Then there's some other elements inside this electron gun that pick up those electrons and shoot them out the holes in the front toward the front of the screen. But that's really all there is to it. There's nothing mysterious about it. Sometimes you can see the glow, sometimes you can't. Just because you're looking down in the neck of the picture tube and you don't see the glow doesn't mean that they're not lit up there. Very often you have to turn off all the lights in the room and really look carefully to see the glow. Sometimes it's really obvious. Well, I've broken one of these electron guns apart here so you can kind of get a better look at the business end of the cathode. And that's what it looks like. You see the 3 cylinders, and those are the actual cathodes. You can't really see the barium coating it because this is it's all been worn off. And in fact, I've never opened up a new electron gun. I don't even know if you can really see it even when they're brand new because it's a very thin layer. It's not very thick at all. So those are the 3 cathodes, and there's one for each flavor, one for red, one for green, and one for blue. So we have these cathodes down in the bottom of the electron gun, and the electron emits a ray or a beam of these real high-energy electrons. And they're really moving. They are just hauling butt. They are just moving really fast at practically the speed of light. See how fast they're moving? Ooh, they're moving really fast. Look at how fast they're going. They're just hauling buns. But because this thing has these cathodes in it, and they emit a ray or a beam of electrons, technically speaking, as you know, a picture tube is known as the cathode ray tube. It's called the cathode ray tube, or CRT for short. Anytime you see the term CRT used in conjunction with a monitor, CRT, cathode ray tube, CRT, what they're talking about is the picture tube itself. The picture tube itself is the CRT. The whole thing is the monitor. That is to say, it's the CRT, the electronic chassis, the metal frame. The whole thing is the monitor. The picture tube is the CRT. For some reason, sometimes people get confused and they want to call the chassis, and the rest of it the CRT, but they don't know which is the CRT and which isn't. So it's the picture tube itself that's actually the CRT. And what really is happening in terms of physics here is this, that these electrons are traveling really fast. These electrons are traveling at practically the speed of light. They have a tremendous amount of what is known as kinetic energy. The energy of motion is kinetic energy. When the electron strikes the phosphor coating on the inside of the screen, that mechanical energy is converted into light energy, and that's what makes the light come out. I think many of you are probably aware that there's a law of physics, it's known as conservation of energy, that kind of states that energy can't be destroyed. It can only be changed from one form to another. Remember Star Trek 16 where Spock gets caught on the ice planet and he has to use his phaser to heat up the... Never mind. So anyway, so you can't destroy energy. You can only change it from one form to another. So in this case, what we have is this kinetic energy that's being turned into light energy when it hits the phosphor coating on the front of the screen. Make sense? Nothing really mysterious about that. And what we end up with then is something that looks like this. Turn this off for just a second. Hopefully what we have is something that looks like this. Let's see. Come over here. Hopefully it looks like this. Uh-oh. Doesn't look like anything. Wow. I knew I should have done this experiment before I came here. Let's try something here. No, hang on just one sec. Oh my goodness, it doesn't work. It's going to shut down. Well, there's a real interesting experiment that I can do in some monitors, and apparently I can't do it in this one for some reason. What the electron gun is doing is it's really just shooting straight ahead. The electron gun sends out a beam of electrons, and they shoot straight out, and all they do really is strike the center of the picture tube here. Normally, I can do this really cool experiment that enables me to show that to you, and it was the one thing I didn't experiment with last night when I set this thing up, and so it figures that it doesn't work. And all the electron gun does, though, is sends out a beam that strikes the center of the picture tube, and all we get is a dot right in the center of the picture tube. Well, that's not very entertaining. It would be nice if we could maybe move the dot around. Unfortunately, the electron gun is fixed in the neck of the picture tube. The electron gun itself can't move around. If we could move the electron gun around, maybe we could use it to draw something on the front of the screen, but we can't because it's fixed in the glass neck of the picture tube. So we have to do it another way. And the way we do it is with magnetism. One of the ways that we can move a beam of electrons around is with a magnetic field. And to do that, there's an electromagnet that sits on the neck of the picture tube. Down here on the neck of the picture tube, there's an electromagnet assembly which we call the yoke. Now, it's actually really referred to as the deflection yoke. Let me just write it on the board here. And I'll try to set up this experiment if I can later on, just to show you. It's very interesting. Since we cannot actually move the electron gun around, somehow what we have to do is instead we have to deflect the beam. And by deflect the beam, what I mean is to push it around. To deflect something means to change its trajectory, to push it from one side to the other. So instead of moving the gun itself, we have to deflect the beam. And to do that, we use this electromagnet assembly, which we refer to as the deflection yoke. That's its technical name. Everyone just refers to it as the yoke. It really is the deflection yoke. And the deflection yoke really consists of two coils. Now, it's actually two pairs of coils, but we can kind of think of it as two coils. Make sure that this is turned off. One of the coils in the deflection yoke simply makes the beam move left and right. That's all it does. It just makes the beam move left and right, as you can see here. Now, you'll notice that we have a horizontal line on the screen, and I do want to make sure that I don't have this too bright. If it's too bright, it will burn the phosphor. You've all seen phosphor burn in a monitor where the image of the game is the reels or whatever it is, the cards are burned into the screen. Once the phosphor is burned, that's it. It's irrevocable. There's no way to fix it. It's burned forever. You have to replace the picture tube. So I want to be careful that I don't do this. They don't burn although it's not my monitor, so what do I care? Now what we have here is a horizontal line. It's really important to realize this is just a single spot, a dot, moving across the screen from left to right, but we see it as a line. And the reason we see it as a line is that the phosphor continues to glow even after the beam has moved off of it. It's something that we refer to as, and you don't really have to know this, it's called phosphor persistence. It's called phosphor persistence as the phosphor persists or continues to glow even after the beam has moved off of it. And you can kind of see this at night, can't you? If you're watching television in your bedroom at night, when you turn off the set, it kind of glows for a little bit. And in fact, you can take a television set in a darkened room, and you can take a little pen light flashlight and kind of drag the flashlight across the screen, and you will get a ghostly trail of phosphorescence that follows it. But it is really important to realize this is just a single dot moving across the screen, but we see it as a line as it goes because of that phosphor persistence. So there's one coil in the yoke that makes the beam move left and right, and of course there's a circuit that drives that. It's known as the horizontal deflection coil. It's called the horizontal deflection coil. The horizontal deflection coil is one of two coils that's in the yoke. It's called the horizontal deflection coil. It is actually a pair of coils. To be perfectly honest with you, it's a pair of coils, but you can think of it as a single coil, horizontal deflection coil. It's called the horizontal deflection coil because whoa, sorry about that. It's called the horizontal deflection coil because it deflects the beam in the horizontal direction, which is the wide direction of the monitor. It's really important to realize, you know how a monitor is wider than it is tall? The wide direction of the monitor is always called the horizontal direction, no matter which way the monitor is mounted. Now, we don't have very many of them in gaming, but you've probably seen Odyssey. Oops, bad word, I know. And if I can do this without, you guys know CPR, right? If I do something bad here, let's see if I can spin this around without destroying something. That is a horizontal line. That's really, really important. Some monitors might be turned sideways. We call it a vertical mount. You would still refer to this as a horizontal line. That's really important. For example, if you were to contact me for technical advice, which you're more than welcome to do anytime. I enjoy helping people on the phone fix monitors. It's something I've always done, and I really enjoy doing it. If you were to call me up and say, "Hey, Randy, I have a monitor with a vertical line on it." Well, actually, if you call me up and say, "Hey, Randy, I have a monitor with a vertical line on it," the first thing I'm going to say is, "Bullpucky, you don't." For reasons that I'll explain later on, you'll see why that would be pretty darn rare. But if you did manage to convince me that you had a monitor with a vertical line on it, which this is not, right? This is not, I would send you to a completely different area for troubleshooting. A problem that would cause a vertical line has absolutely nothing to do with a problem that would cause a horizontal line on the screen. They are two completely different things, totally unrelated. Is everybody with me on the fact that this is a horizontal line? The wide direction of the monitor is always called the horizontal direction. It happens to be, and you kind of really don't need to know this, it happens to be referred to as the aspect ratio of the monitor. Let me just write it on the board here. In a kind of a standard monitor like this one, the aspect ratio, as it's called, you don't really have to know this, but it's something to know, is 3 to 4. Or 1.33 to 1, if you will, 3 to 4. The wide direction, the 4 direction, is always called the horizontal direction, no matter which way the monitor is mounted. Now, as many of you are probably aware, if you've been to any kind of an electronics store recently, you see these new widescreen monitors, which is what high-definition television is going to be. What they did was they squared both of these dimensions. Instead of 3 by 4, it's 9 by 16. And that will be the new standard for television following the year 2006, in fact. They're going to start transmitting what's known as high-definition television. Well, they do now. But by the year 2006, all television will be high-definition television. And if you have a regular TV now, you're either going to have to get some kind of a set-top box that's going to convert it to regular TV, which is what we call NTSC, as I mentioned before, or you're going to have to buy a new television. And so you'll see more and more of these. I do a lot of world travel in Asia and in Europe, and you don't find these 3 by 4 ratio TVs at all anymore there. Anywhere you go, airports or stores or anything, it's all the 16 by 9 aspect ratios is what they're using now. But be that as it may, we're still at 3 by 4 for the most part. So the Y direction is called the horizontal. So one of the coils in the yoke simply makes the beam move left and right, and it draws that line as it goes. It really is just a single dot, or, if you will, combination of 3 dots, red, green, and blue, as it moves across the screen. But we see it as a line as it goes because of that phosphor persistence. There's another coil in the yoke that just makes the beam move up and down. Golly gee whiz, guess what we call it? Vertical, the vertical deflection coil, right? So there are 2 deflection coils in the yoke, the horizontal deflection coil that makes it move left and right, and the vertical deflection coil that makes it move up and down. Well, if I can make the beam move left and right, and I can make it move up and down, I should be able to put that beam anywhere I want on the front of the screen, and I can. Now, all I did to get those horizontal line on the screen was I simply disconnected the vertical deflection coil in the deflection yoke. Here's the deflection yoke itself, and I showed it to you earlier. You can kind of see the coils of wire on the outside of it. Not so visible in this one as it is in some of them. And all I did was disconnect the connector here. It's kind of a standard connector that we use for connecting the yoke down here. And you can see how I have one of these disconnected. That's the vertical pair, because we just ended up with the horizontal line. It's kind of important to know these colors. There are 2 different pairs of coils, and so we have 2 different colors. These are fairly standard. The red-blue pair that you see here, that's the horizontal pair, red-blue, and either brown-yellow or green-yellow, depending on who makes it, but typically it's brown-yellow now, is the vertical pair. So this is for the horizontal deflection coil. This one's for the vertical deflection coil. You can't mix them up because they are keyed or different widths. You can see the spacing between the 2 pins on the left. The horizontal coil is wider than the vertical pair. So unless you use a big hammer, it's really hard to get them in there wrong. It's possible. I've seen it. But it required lots of bending and tweaking, and I don't know why anybody would have done that, but they did. And what we end up with is this. Just a screen full of white light, no actual picture. Now, again, because of the scanning nature of the way the camera scans versus the way the monitor is scanning, we see that's this weird black bar, which doesn't really exist. Or for those of you at home, really here, it doesn't really exist. Just a white screen like this. And when we have a white screen like this with no real picture at all, just a white screen, this is known as raster, R-A-S-T-E-R. It's called raster. This is known as having raster. It's important to be able to tell that you have raster because it means that certain things in the monitor have to be working okie dokie. For example, in order to have raster on the screen, the horizontal deflection coil in the yoke and the horizontal deflection circuit that drives the horizontal deflection coil in the yoke, that has to be working. Likewise, the vertical deflection coil in the yoke and the vertical deflection circuit that drives it also has to be working. Otherwise, all we'd see is that horizontal line that I showed you before, because the vertical makes it move up and down. Likewise, in the monitor, there is a power supply. In a monitor, there's a power supply that we're going to take a close look at in great detail. It happens to be referred to as the B+ power supply. And don't worry about it. We'll take a look at it in really great detail. Typically, it's anywhere from 77 volts DC to about 125 volts DC or so, depending on the type of monitor that it is that you have. This B+ power supply also has to be working. Because if the B+ power supply, which is the main power supply in the monitor, wasn't working, we wouldn't see anything at all on the front of the screen, would we? So just by looking at the monitor and seeing that we have this thing that we call raster, it tells me that certain things in the monitor have to be working okie dokie. When somebody contacts me for technical advice, and let's say that's their symptom, blank screen. one of the first things I'll ask them to do is reach into the back of the monitor and crank up the main brightness control in the monitor. In a monitor, the main brightness control sits on the flyback transformer, the high voltage unit here. Only it isn't labeled brightness. It's called the screen control. There's the high voltage unit here, and this particular monitor, the slant top monitor, is turned sideways, so really, whoops, the way you sorry. The way you normally see it is turned sideways like this. The bottom control is called the screen control, and I don't know if you can read it or not. If you look real carefully, it says screen on the top of it. It's kind of covered with some white goop there. So one of the things I'll ask them to do is reach in the back of the monitor, crank up the screen pot like this. You know, do you see raster come up when you crank up the screen pot? Do you see raster? Well, in this case, we do. And so that means that certain things in the monitor have to be working okie dokie. So just by cranking up the pot and seeing that we have raster on the screen, right away we know that the B+ power supply is okie dokie. We know it exists at least. We know that the vertical deflection coil that makes the beam move up and down and the vertical deflection circuit that drives it is working. We know that the horizontal deflection coil in the yoke and the horizontal deflection circuit that drives it is working. And this is how you repair the monitor. And you'll see this as we go along. When you see a monitor problem, instead of looking at that problem and agonizing over it and saying, oh my God, what can possibly be causing this problem? Instead, we kind of look at the symptoms, eliminate the things that cannot possibly be the cause of the problem, and anything that's left you have to test. In other words, if this happens to be my symptom, where I just have raster but no actual picture, whatever's wrong, I know it's not the B+ power supply, it's not the vertical deflection circuit, it's not the horizontal deflection circuit. Whatever that problem is, it's not that. I'm not going to look at those things. And as we go through the class, you'll see what I'm talking about. Let's take a break. Alrighty then, let's see how it actually makes the raster on the front of the screen. The beam, or the beams really, because there are actually three, but let's just call it the beam, starts out in the upper left-hand corner. Now, it actually really starts out in the center. Remember, the electron gun is fixed in the neck of the picture tube, and it's really shooting right out at the center. So where the beam is really aimed at the beginning is in the center. But where it first appears is really in the upper left-hand corner. In other words, the vertical deflection coil in the yoke and the vertical deflection circuit that drives it, and I'm kind of repeating these terms so you get used to them, starts the beam up at the top. The horizontal deflection coil in the yoke and the horizontal deflection circuit that drives it starts the beam at the left-hand side. And when the beam first appears, it's in the upper left-hand corner. Then the horizontal deflection coil in the yoke and the horizontal deflection circuit that drives it makes the beam move from left to right, and it draws a line as it goes. Now really remember, it's just a single dot moving across the screen, or a combination of three dots, red, green, and blue. But we see it as a line because of, remember, the phosphor persistence as it continues to glow. When the beam gets to the right-hand edge of the screen, it is turned off. The magnetic field in the yoke resets to bring the beam back to the left, and when the beam next appears, it's at the left-hand side, and it draws another line from left to right. It only draws these lines from left to right. These lines, which are referred to as raster lines. Each one of these lines is known as a line of raster, or a raster line, and it only draws these lines from left to right. When the beam gets to the right-hand edge, all three guns are turned off. The magnetic field in the yoke flips to bring the beam back to the left-hand side. When it's back over on the left-hand side, it turns on again and draws another line from left to right. It only draws a line from left to right because if it drew a line on the way back, we would see a diagonal raster line in between each of these parallel raster lines, and the picture would look all washed out and really, really funky looking. It would look just terrible. So we don't do it that way. It only draws a line from left to right. Now, in a standard television, like your home television or a standard resolution monitor, in what we refer to as NTSC resolution, and we'll talk more about resolution as we go through the class, it takes 50 microseconds, and this letter that I've drawn here is the Greek letter mu, which means micro, which means 1/1,000,000th. Let me just zoom in on it so you can see it for those of you who have never seen the Greek letter mu. That's what the Greek letter mu looks like, just to draw it real big. Like that. And that means 1/1,000,000th. So it takes approximately 50 well, it takes exactly 50 microseconds, 50 millionths of a second for the beam to move from the left side of the screen to the right side of the screen. Now, that may seem pretty fast, but it actually comes back even faster. It comes back in only 13 microseconds. It only takes 13 millionths of a second for it to move back. So what the beam does is it moves more slowly from left to right across the screen, and then it quickly moves back to the left. Draws a line from left to right, and it quickly moves back to the left like that. Well, this time period, when the beam is at the right-hand edge and has to quickly move back to the left, has a name. It's called the retrace. Or, more technically in this case, this is known as the horizontal retrace. It's called the horizontal retrace, as essentially what the beam is doing is it's retracing its step. In other words, it starts on the left-hand side here and draws more slowly from left to right. Okay, drawing a line from left to right, gets to the right-hand edge, and it quickly retraces its steps back to the left-hand side. Moves more slowly from left to right, and then quickly retraces its step back to the left-hand side again. But during this time period, during the horizontal retrace time, when the beam is at the right and has to quickly come back to the left, we don't want to see a zigzag, a diagonal line in between each of these parallel raster lines. So all of the guns are turned off during that time period. And there's a circuit in the monitor that does that. And it's called the blanking circuit, B-L-A-N-K-I-N-G. It's called the blanking circuit. And what the blanking circuit does is the blanking circuit turns off all 3 electron guns during the retrace time. When the beam is at the right-hand edge and it has to quickly come back to the left, we don't want to see that diagonal line. So we have this blanking circuit, and the blanking circuit turns off all 3 of the guns during the retrace time. When the blanking circuit is on, the guns are off. Everybody with me on the concept there? When the blanking circuit is on, the guns are turned off. So the way it works is, it starts on the left-hand side, draws a beam from left to right, then we get blanking and then retrace. Then it draws the next line from left to right, blanking, retrace. Draws the next line from left to right, blanking and retrace. Now, the whole time that the horizontal is doing this, the vertical deflection coil in the yoke and the vertical deflection circuit that drives the vertical deflection coil is making the beam move from the top of the screen down to the bottom of the screen. That's how we get one line underneath the previous line. Remember, the horizontal is just going left and right. I showed you that on the monitor, just that horizontal line right down the middle of the screen. That's all it's doing. The vertical starts it at the top and pushes it down so we get one line underneath the other one. And it's a continuous process. It is not like it draws a line and then cha-ching goes down to the next one and cha-ching down to the next one. It is always continuously pushing down. So the beam actually moves down at a real slight angle. Now, it's so slight that you can't see it. And in fact, the actual yoke is rotated to compensate for that, you can actually see it here. If you look carefully at the raster, and in fact, let me just change the pattern just a little bit here to make it obvious. I can reach in the back and grab the yoke and rotate it a little bit. Can you see how I'm moving, tilting the raster just a little bit? You can see how it's moving back and forth. All I'm doing is moving this yoke a little bit back and forth. So it's actually rotated just a little bit to compensate for it. You don't see it. I'm going to exaggerate the heck out of it here. As the horizontal is going from left to right, the vertical is pushing down, and the beam actually moves down at a slight angle. Nowhere near that steep. But that's how, when we get the horizontal retrace that quickly brings the beam back to the left-hand side, see how it ends up underneath the previous line. So then it draws the next line. We get the retrace, it brings it back to the left. And it draws the next line, and the next line, and the next line, and the next line, and so on, until eventually the whole screen is filled with these parallel raster lines. And when we have that whole screen filled with lines like that, again, it's what we call having raster. This is known as having raster. One complete pass of the beam from the top to the bottom, one screen full of lines, is known as a field, F-I-E-L-D. It's called a field. So starting at the top, it draws all these parallel raster lines until it eventually fills the whole screen with these white lines, which we refer to as having raster. The term actually comes from the Latin word rastum. You don't really have to know this. Rastum in Latin, which means to rake. To rake. As the electron beam rakes across the face of the CRT. I mean, if you think about it for just a second, if I took like a sandbox that was perfectly flat and just put a rake on it and just dragged it across, isn't this what I'd end up with, a whole bunch of parallel lines like that? And so that's where the term raster scan came from. I was wrong. When I first started working on monitors, I thought that this was invented by a Jamaican guy. But that's a Rasta scan monitor. That's something completely different. All right. So anyway, so that's why it's called a raster scan monitor, if you care, and you probably don't. So eventually we have this whole screen filled with lines, and just so we don't get confused, let me just kind of make it a little more parallel-y here. Like this. And now the beam is down here in the lower right-hand corner. Well, obviously, if the beam is at the right-hand side of the picture tube, we can't go any further to the right, so it's time for the horizontal retrace that's going to bring it back to the left-hand side. But the beam is also at the bottom of the screen here. Obviously, we can't go any further down. So now it's time for the vertical retrace. And the vertical retrace brings the beam from the bottom of the screen back up to the top of the screen. Well, if you think about it for just 1 second, if I have a horizontal retrace that brings the beam from the right side back to the left, and I have a vertical retrace that brings the beam from the bottom of the screen back up to the top, the effect is going to be that the beam is going to end up back up here in the upper left-hand corner, which it does. And before this has a chance to fade from view, it does this over and over and over again. In other words, it refreshes it back up again. It draws one field. Remember, one complete pass of the beam from the top to the bottom is called a field. Now the beam is here. It ends up back up here in the upper left-hand corner and does this over and over and over again. It does this 60 times a second. The monitor paints 60 fields per second. In other words, every 60th of a second, it's refreshing itself over and over again, rebrightening it before that phosphor has a chance to fade. The frequency of our vertical deflection circuit that drives the beam up and down is 60 cycles per second. 60 cycles per second, better known as 60 hertz, named after a guy named Heinrich Hertz, not the guy you rent the cars from. So the frequency of the vertical section is 60 hertz. Well, that's the same frequency as our AC power, isn't it? Our AC power is 60 hertz. No coincidence there that it is. However, this is really important, the monitor does not depend on the AC power to get that 60 cycles per second or that 60 hertz for the vertical deflection. It is generated internally inside the monitor by a circuit that we'll look at in tremendous detail called the vertical oscillator circuit. Don't worry about it. Don't write it down. Don't worry about it. I'll cover it in great detail later on. You'll know everything about the vertical deflection circuit when we're done with this. But it is the same frequency, and they made it that way intentionally. But the AC power is not used to get that vertical deflection, which is also known as vertical sweep, by the way. Deflection and sweep are both used interchangeably, SWEEP, sweep, as the beam sweeps across the screen from top to bottom or sweeps across the screen from left to right. It's called sweep or deflection. If the monitor depended on the AC power to get that 60 cycles per second, you couldn't have battery-operated TVs, could you? And you know that we do have battery-operated television. So it's generated internally. We'll take a look at where it comes from later on. So every 60th of a second, this thing is constantly being brightened and refreshed over and over and over again. Now, monitors have gone through somewhat of an evolution in that their resolution has changed. And what I'm talking about when I say resolution is the number of lines that actually make up the picture. The more lines you can get on the screen, the more raster lines, the better the resolution. The higher the resolution. The more lines you have, the higher the resolution. So, like for example, an NTSC, if we were talking about standard NTSC television, like the standard television that we use for your home TV, now anyway, NTSC. NTSC happens to stand for, you don't need to know this, absolutely don't need to know this, it happens to stand for National Television Standards Committee. It's the television standard we use in the United States, and we've used it in the United States for more than 50 years. This television standard was developed in the late 40s, and it's gone through some modifications. For example, we added color television and some other things, but basically it's the same circuit that we've been working on for 50 years. In a standard NTSC television, the picture is made up of 525 lines. That's how many lines that make up the picture, of which only 480 are actually visible. There's some invisible lines there that you don't see that happen during the vertical retrace time. When the beam is at the bottom of the screen and has to come back up to the top, it takes a long time for that to happen, almost an eternity in terms of electronics kind of stuff. And during that time period, there are some invisible lines there that you don't see. And so what you see on the screen, what's actually on the display, is really only 480 lines. Now we first started making video poker games and Player's Edge Plus and stuff like that. And they used a monitor that was the same resolution, basic resolution as NTSC. It's something that we refer to in the computer business as CGA resolution, which happened to stand for Computer Graphics Array, CGA. And you can kind of see it here on my little pattern generator that I'm using. Here on this little pattern generator, if you look at the different resolutions I have available to me, you can see one of them is called CGA. This is a pretty cool little pattern generator. It's made by Wells Gardner. It's like $250 or something. It's really a cool little thing. It works off of a 9-volt battery. It's a great tool. Available from American Gaming and Electronics. Available from Hap Controls, I think, or Wells Gardner. You can call them directly. Hey, there's their phone number. How about that? Anyway, CGA resolution. And the first games that came out that used the CGA resolution really only showed you half the number of lines. The CGA resolution was only 240 lines. Regular television, your home broadcast TV, uses a very interesting scheme to show you these 480 visible lines. It doesn't show them all at once. A regular television uses a scheme which we refer to as interlaced raster. I'll write it on the board in just a second. Let me just change the pattern. the way regular standard broadcast NTSC television works is it sends out odd and even fields. On the first pass of the beam, from the top to the bottom of the screen, it lays down lines 1, 3, 5, 7, 9, 11, 13, and so on. Then the beam goes to the bottom, comes back up. On the next pass, it lays a raster that's interlaced, that is lines 2, 4, 6, 8, 10, and so on. It's called interlaced raster. And when they first made television, they really had to do it that way because of the limit of the electronics themselves. That is, there was a limit to how fast you could make the yoke respond and how fast the electronics worked, which was, of course, all vacuum tubes back when they first made television. So it was really the only way that they could actually get enough lines to make a nice picture. Remember, the more lines you have on the screen, the nicer the picture looks. The higher the quality the picture looks, the better the resolution. So that was what they did to get the 480. So then we made this Player's Edge Plus game with this CGA monitor, and they just figured, well, look, you know, it's just a poker game. We don't have to show really high-quality graphics. We'll just use 240 lines. And if you look at the very first video poker games, there's still some in operation with their original Ceronics monitors in them out there. And you look at the graphics, and they're real blocky, aren't they? They're cartoony looking. They're not very sharp and clear because there's not very many lines on the screen. The more lines we can have, the better the resolution is. So we started out there. Then the next thing they did was they improved the resolution slightly. In the computer business, they called this EGA resolution, and I can't recall that there were any slot machines that used EGA, but there might have been. And that had 400 lines of resolution. That is to say, we put 400 lines in the same space as we had 240 before. Well, if I can put 400 lines in there instead of just 240, I can show smaller objects with better clarity. So they did that. Then the next step up was something we're all familiar with, known as VGA. Video Graphics Array is what it happened to stand for. And like VGA resolution is like 640 by 480. Now what 640 by 480 means is that in a VGA monitor, which is what this one is running at right now, that the monitor can address or illuminate up to 640 individual dots along one line. Individual, what we call picture elements, or pixel for short. A picture element or a pixel. In other words, the computer can tell the monitor to turn on and off any one of 640 dots along one line and make it any color that it wants and make it any brightness that it wants by 480 lines. So in your VGA monitor, which you might have running on your computer at home, it can address 640 pixels by 480 lines. If you did a little bit of 640 points by 480 lines. If you did the math, you might have realized that 640 by 480 is 4 by 3. That's the aspect ratio of the monitor, isn't it? And you'll find that that's always true. So then there's another resolution. We went up even higher than that. And again, if you have a computer at home, you know that there's what we call SVGA, Super VGA, which is 800 by 600 resolution. And that's, again, and it's obvious that it's a 4:3 ratio there, isn't it? That is 800 pixels by 600 lines. And again, as we go up and higher in resolution, you get a higher and higher quality image. So if you look at my pattern generator here, again, you see that we have a CGA resolution. The next one was called EGA, and after that it was VGA, which is 640 by 480, which is where this one happens to be running at the moment. And then you can go up to Super VGA, 800 by 600. And there's even Super VGA 1024 by 768, which is where my computer at home happens to be right now. And you can see it even goes up to 1280 by 1024. It goes bigger than that, actually. Modern monitors, if you're on a CAD CAM system, it might be 1200 by 1600 resolution. All right, so let's go back to this one here. Let's start with the CGA resolution and work our way up here. Think about this for just 1 second. Remember I mentioned that the frequency of the vertical deflection circuit is 60 hertz. Well, if this monitor, let's say the CGA monitor, has to draw 240 lines, while the monitor paints just one field, the horizontal circuit must be working at a much higher frequency than the vertical frequency. So, like in a standard resolution monitor, if we were talking about NTSC here, these guys, while the vertical is stuck at 60 hertz, the horizontal frequency here is 15,750 hertz, or some people might refer to it as 15 kilohertz, 15,750 hertz. So that's a whole lot faster, obviously. You can see what I'm talking about. 15,750 hertz. Some of you can hear that high-pitched squeal. Occasionally when you get to a monitor, you first turn the monitor on, you can hear kind of a high-pitched squeal that it makes. Not always, but sometimes. And you can only hear that on a standard resolution monitor. If you hear that squeal, what you're hearing is the 15 kilohertz or the 15,750. And really, if I really wanted to be really truly exact about this, and if we were talking about NTSC, this is for those of you that might be the hot shots here in the audience, don't write this down, it's really 15,734 hertz if we're really talking about NTSC. But everybody just calls it the 15,750 or the 15 kilohertz. Well, let's ignore EGA for the moment. Let's go up to... Okay. Let's go up to VGA here, where CGA shows us 240 lines, VGA shows us 480 lines. Gee whiz, how are we going to accomplish that? It turns out to be really simple. All we have to do is double the horizontal frequency. While the frequency of the horizontal section is 15.750 in the CGA monitor, for VGA it's 31.5 kilohertz. If I can make the horizontal circuit work twice as fast, I can get twice as many lines in that same 60th of a second, can't I? So that's all they do, is they just simply increase the horizontal frequency so that we get more lines in the same period of time. Typically, the vertical frequency, it's sometimes referred to as the refresh rate, is typically stuck at about 60. Although that is adjustable, and either the person that designs the game, the manufacturer, can adjust that. Or, for example, if you have a home computer and you have a fairly sophisticated computer graphics array and or monitor, as you may know, if you go into the Windows desktop settings, you can set the refresh rate. You can set it to be 60 hertz or 70 or 72 or 75. Theoretically, the faster you can make it refresh, the less flicker you will see on the screen. But quite frankly, I don't see any flicker at 60 hertz. I don't know if anybody does. Kind of weird, though, if you go to Europe, in Europe, they use a different television system. It's called PAL or CCAM, and instead of our refresh at 60 hertz, they refresh at 50 hertz. Their AC power is also 50 cycles per second or 50 hertz. And it's very unusual when you go to Europe for the first time and you look at the television, you will definitely see a noticeable flicker. You'll look at it and you'll see it flickering, and after you've watched it for about 5 or 10 minutes, you can't see it anymore. It goes away. Somehow your brain kind of compensates for it, so it's kind of a weird deal. But anyway, so all we have to do is increase the horizontal frequency. Well, the point that I'm really making is this. When the beam was in the lower right-hand corner, I said to you that we get the vertical retrace, and it brings the beam to the top, and the beam ends up in the upper left-hand corner. Well, I kind of lied to you. I didn't really lie to you, because what I said was it ends up in the upper left-hand corner, but I implied that it goes directly. It does not, actually. The vertical deflection circuit's working really, really slowly compared to the horizontal deflection circuit. By the time that slowpoke vertical gets the beam from the bottom of the screen back up to the top of the screen, the beam has actually gone back and forth about a dozen times like this. It really winds its way back up to the upper left-hand corner. But we're not supposed to see these lines, these zigzaggy diagonal lines here. We don't want to see them because it'll make the picture look terrible. And so we don't see them, and the reason we don't see them is because of this blanking circuit. Remember, the blanking circuit turns off all three guns during the retrace time. Not only during the horizontal retrace, when the beam moves from the right side of the screen to the left side, but maybe even more importantly, when the beam is at the bottom of the screen, we don't want to see these zigzag lines that go across the screen, which have a name. They're referred to as vertical retrace lines. This is important that you know. They're called vertical retrace lines. Vertical retrace lines. These zigzaggy lines are referred to as vertical retrace lines. Now, I may be able to invoke these here. Let's see if I can. Sometimes I can make those appear just by cranking up the brightness really high. Now, as some of you are aware, most of the slot monitors that we use these days have a kind of an automatic brightness compensation. It's known as auto bias. So this may or may not work. Let's see. And you might have to look carefully and see, and watch the screen carefully. And they may only appear for just a moment. So let me just put this on a raster here. And let's see what happens when I crank this up. Did you see for just a moment the vertical retrace lines? Watch the screen carefully. You may not even see it on the monitor. Did you see them there for just a second? Now, if this was not an auto-biasing monitor, I could actually have them there and leave them there. But because as soon as I turn up the brightness, the monitor goes, whoa, holy cow, and it turns the brightness down on me. So watch it carefully. I'm going to whip it up. Did you see them there for just a second? So those vertical retrace lines, they always look like that. They always appear to go from the lower left to the upper right. And then sometimes, depending on the monitor, you might see a faint little line coming back and then up like this. Did you notice, however, that those lines were white? They are white. We're going to talk more about this as we go through this thing later on. If you have vertical retrace lines, it means you have some kind of a problem there. The blanking circuit is supposed to turn off those vertical retrace lines. Now, they are not vertical lines, obviously. They are zigzag lines. I mean, if I dragged some kid off the street and said, hey, what do you think a vertical retrace line looks like? He would go, well, it would look like this, wouldn't it? You know, because it's called a vertical retrace line. But it's not a vertical line. It's a diagonal line that appears during the vertical retrace time. That's why we call it the vertical retrace lines. They call them vertical retrace lines. And what's interesting about this is that a lot of people, knowing that they are called vertical retrace lines, mistakenly believe that when they see these zigzag lines, it means that something is wrong with the vertical deflection circuit in the monitor. Mistakenly believe this. Nothing could be further from the truth. If your monitor is filled out totally from the top to the bottom, completely like this, your vertical deflection circuit must be okay, mustn't it? Because the vertical deflection circuit is the thing that's responsible for moving the beam up and down. But because they're both called vertical retrace lines, vertical deflection, people mistakenly believe that it's a problem with the vertical deflection. And in my lab, I've had people bring me monitors where they'll bring me a monitor and they'll go, hey, Randy, man, we've replaced every part in the vertical deflection circuit. It still has vertical retrace lines. Well, no kidding. You know, I mean, replacing good parts doesn't ever fix anything, right? So it's important to realize that if you have those vertical retrace lines that I showed you, you have a problem not with the vertical deflection circuit, but perhaps you have a problem with the blanking circuit. Remember, the blanking circuit is the thing that's supposed to turn off all the guns during the retrace time. If your blanking circuit is inoperative, you'll see the vertical retrace lines. And they will be white because the blanking circuit controls all three guns simultaneously, right? All three colors together make white, don't they? So that's real important. Later on in the class, I will probably show you some vertical retrace lines, but they'll be red, green, or blue. And that is definitely not a blanking problem. Now, although this is a logical assumption that if you have vertical retrace lines, you might have a blanking problem, in point of fact, the blanking circuit is actually really reliable. The blanking circuit doesn't work very hard. Ray, have you ever fixed a blanking circuit problem? Never. And I've fixed like 2 or 3 in 30 years. So the blanking circuit probably really isn't your problem. What really happens in our environment is that the picture tube wears out. What happens is, over a period of time, the gun wears out. And in these auto bias monitors especially, they're always monitoring what we refer to as the beam current, the amount of electric current that the actual electron beam is drawing. And as the electron gun starts to wear out, the monitor circuitry starts boosting things up. And it keeps boosting things up, and the more that the electron gun starts to diminish in its emission, the more the circuitry boosts up its drive circuit, so to speak, to get it to be proper brightness on the front of the screen. Eventually, it turns the brightness up so high that it's kind of just like what I did over here by turning up the screen control to show you the vertical retrace lines. It just cranks up the monitor so high that it's overcome the blanking circuit, and then you see the white zigzag vertical retrace lines on the screen. If you see, in the casino industry, if you see vertical retrace lines on the monitor, either you simply have it adjusted too bright and you have to bring it down, which is not very likely, or much more likely, the CRT itself is on its way out, or, well, it's on its way out. Now, when Ray shows you, if you attend Ray's seminar on Sencor, Ray, you're going to show the CR7000, I'm hoping, because that's the best thing Sencor has as far as I'm concerned. They have this really cool piece of test equipment that Ray will show you called the CR7000. It's a CRT rejuvenator that has a very high success rate of taking these monitors that are dim and maybe you have the vertical retrace lines on them, and it's something called shooting the tube, rejuvenating or shooting the tube, and it can brighten it back up and give you 6 months or a year of extra life, or not. Depends on how bad the picture tube is. So, but you will see those vertical retrace lines sometimes. How many of you have seen those on something? So, yeah, most of you have. Okay, so anyway, so not so unusual. Okay, so that's really what's happening. So the beam comes back to it zigzags its way to the upper left-hand corner, and then repeats the process over and over again 60 times a second. Everybody with me so far? Pretty simple, right? Okay, so what we end up with is just this raster right here. Well, I don't know about you guys, but unless it's the White Rabbit in the Snowstorm slot game, it's kind of not very interesting. You can see the phosphor burn. I'm not sure if we can see it on the. Oh yeah, you can definitely see it. Look at the monitor. See the phosphor burn, and that's irrevocable. Once it's burned, there's nothing you can do about it. I had one guy tell me, oh yeah, man, the way you fix the phosphor is you crank the brightness all the way up like this, and you take it outside in the hot desert sun and sit it face up in the sun for a day, and that'll cure the phosphor burn. Not. All right, so, but once it's there, you know, there's nothing you can do about it, but it's pretty obvious. And the funniest symptom I ever got, I went on a service call, and this was the symptom, but this isn't what the location said. The complaint was, you know, I said, well, what's wrong with it? And I said, does it have a picture? She said, yeah, it has a picture, but it's real dim. And so I'm thinking, what could cause a real dim picture? But when I came back out, it was this. It was no picture at all, just raster with the phosphor burn, and that's all it actually was. So all right, so anyway, but that is not a very interesting game. It would be nice if we could maybe draw some kind of a picture on the screen, and since turning things on and off, turning the guns on and off is what makes the areas of the screen bright and dark, all we have to do is turn the guns on and off at the right times, and maybe we can draw some kind of a picture on the screen. So let's see how that works. So there's some kind of a picture tube. Looks kind of like a cross between a standard and a high-resolution tube, but that's okay. Let's just say, for the sake of discussion, that we want to have a white square in the middle of the picture tube. It's black all around with just a white square in the middle. Now, at the moment, I'm working with a black pen on a whiteboard, so let's kind of think negative for just a few seconds here. No matter what we want to draw on the screen or not draw on the screen, that scanning thing that I just outlined to you is always happening. The deflection circuits are always working in that same way, no matter what we want to show on the screen or even not show on the screen. Even if the screen was black for a moment as it faded from the game to the bonus game, that scanning is always happening. That never, ever, ever, ever stops. Not even for a split second. If that ever stopped scanning for a split second, if it like tried to hold the beam in one spot, it would instantly blow the fuse and vaporize stuff in the monitor. That's always happening. Also, you should know, this is really important, that the electron gun has absolutely nothing to do with the deflection coil in the yoke that makes the beam scan. Absolutely nothing. They don't talk to each other in any way. They don't even typically they don't even share the same power supply. Although in one case it does. But typically they are completely independent. They don't talk to each other in any way. The electron gun doesn't know what the deflection coil in the yoke is doing, and the deflection circuits don't know what the electron gun is doing. They are totally ignorant of each other. So let's say that we want to have this white box in the middle, but it's black all around. As the magnetic field is doing its thing, making the beam move from left to right, in fact, the beam really isn't there. It's turned off. But the yoke doesn't know that. It doesn't talk to the electron gun. So it's happily doing its magnetic field, making what it thinks is the beam move from left to right, but it isn't really. Of course, the beams are always off on the way back, but the beams are off during this time. Remember, it's black all around here with a white box in the middle. So it's off, it's always off during the retrace time. It's off, it's off, it's off. It's off, 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 or it wants to start drawing the box, it draws a line segment like that. Then it turns off, it's always off during the retrace time. Then it draws the next line, goes to the end, comes back, draws the next line, goes to the end, comes back. Just like this. Well, heck, this is the same way your computer printer prints, doesn't it? I mean, really, that's all the print head is just moving like this, left to right, and the paper moves. Well, in this case, instead of the paper moving, we move the beam down. But that's all it's doing. Your printer is a raster scan printer, in a way, really. So eventually, we end up with these lines. Now, of course, in the real world, these lines are much more closely spaced than I've drawn them on the board here. But certainly to those of you back in the back of the room, back there, this looks like pretty much of a solid box to you. So now we're done drawing the box. We're done drawing the box, but we cannot stop here and draw the box again. We cannot stop here and draw the field. We can't go back to the beginning of the field. We have to complete the field. That never changes. So we want it black here, though, so the beam is kept turned off as it does this. Now the beam is in the lower right-hand corner, and of course it has to zigzag its way back to the upper left-hand corner, which it does. And then, before that box has a chance to fade from view, it starts that same process all over again. In other words, a 60th of a second later, before it fades out, it's refreshed. The beam is off, 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 off. When it gets to the exact same place, and I mean precisely, perfectly, exactly the same place, it draws another line right on top of the previous line, brightening it back up. Goes to the end of the line, comes back up, draws the second line, the third line, and so on. And it does that over and over and over again every 60th of a second. It's refreshing it, brightening it up before it has a chance to fade out. But it is extremely precise. I mean, it's perfectly precise because you can imagine if it drew that box in even a slightly different place each time, like if it drew the box over here the next time and over here the next time, that box would jitter and jump all over the place, wouldn't it? So it doesn't do that. It shows you something that's in exactly the same place every time, just like, well, any of these displays that we see here. I guess, you know, there's a box. Kind of, sort of, you know, like that. Make sense? Okay. Well, you know, again, none of this stuff is really even interesting either. I mean, I'm not going to play this game either. Maybe it would be neat if we could make something move on the screen. One of the cool things about video slots is animation. One of the cool things is that we can make things move around. Not only the reels themselves spinning, but within the reels they do little animations, and you ain't seen nothing yet. I mean, they've only just barely started to scratch the surface of what they can do. It's mostly just a matter of getting some good graphic designers in there. So let's say that we wanted to make something move on the screen, and you can tell I'm not much of an artist, so let me just draw a little dancing cherry here on the screen. So let's say we have during a bonus game, we want to make a little cherry dance around. So let's say first the computer would draw the cherry here. Now, remember the cherry really has to be drawn one line at a time. So in fact, what we're really looking at is, as the beam is moving from left to right, it's drawing a little line here, and make that green probably because it's a leaf. Draw that here. Then it would draw the lines. Go to the end, come back. It would have to draw it really one line at a time, like this. So first it draws the cherry there. Goes to the end of the field. On the next field, it comes up here, and it draws the cherry over here. Goes to the end, comes back over here. The next field, it draws the cherry over here, and it seems to have expanded a little bit. But you get the point that it's moving across the screen. If the computer wants something to move more quickly, it simply moves it further each field. If it wants something to move more slowly, it just moves it less each field. But really, all this is animation. It's just like in a motion picture or a cartoon where, like in a movie, you'd see an image of a person and he'd be here. Then the next frame in the movie, he's here. The next frame, he's here. The next frame, he's here. And you put it together fast enough, and it's kind of fairly fluid motion. The only difference is that in a movie, it shows you 24 frames per second, and it does show you the whole slide all at once. That is to say, the shutter opens, it broadcasts or sends out the whole picture all at once on the screen. The shutter closes, the film moves, the shutter opens, shows you the next picture, and so on. It does that 24 times per second. With a monitor, it shows you 30 fields per second, and instead of showing you the picture all at once, it does have to draw it one line at a time, but it happens so fast we can't see that happening anyway. Does that make sense? I mean, that's really all there is to that. Any questions about that so far? No? Okay, let's take 10. In the game, obviously the thing that's sending the colors to the monitor is the computer board itself. The CPU, the computer board, the logic board, whatever you want to call the thing. The graphics output, the graphics adapter of a Williams game, whatever you want to call it. It comes from the game itself. There are 3 signals that come out of the computer board that go into the monitor. And these are the color signals. So there's a red signal that comes out of the CPU, it goes into the monitor, and there's a green signal that comes out of the CPU that goes into the monitor, and there's a blue signal that comes out of the computer that goes into the monitor, and all these are changing voltages. That's all they are. The higher the voltage is, the more of that color appears on the screen. So for example, let's say that we wanted something to be, let's say, bright red on the screen. The computer puts voltage out the red wire. If it wanted to be bright red on the screen, it would put out 0.710 volts, just under 3/4 of a volt, to the monitor. I know that seems like an odd value, 0.7, what's up with that, but that's what it is. It's the same standard in your computer monitor at home. In fact, any monitor that you see that uses what's called the 15-pin sub-D connector, let me just show this to you, uses the same standard. This is a real standard connector. This is what's called a 15-pin sub-D connector. Same connector that you have on your computer at home. Anytime you see a connector like that, that is that same thing. 0.71 turns it on. For those of you that are a little hip to electronics, that 0.7 figure makes sense to you because you know that that's the voltage it requires to turn on a transistor. To turn on a transistor, it takes 0.7 of a volt to turn it on. If you don't know anything about transistors, I have a 2-week casino school class that you might be interested in. But enough of that. Okay, so all these are changing voltages. If the computer wants something to be bright red on the screen, it may put out, let's say, 0.7, and we'd see red on the screen. If it wanted something to be red, but maybe not quite so bright red, it might put out only 0.5 or half a volt. It would still turn on the red gun, it just wouldn't be quite as bright. It might be 0.2 here, 0.1, and of course, 0, it's off completely. And it's the same thing for green, and it's the same thing for blue. If the computer wanted something to be magenta on the screen, magenta, this color right here, magenta, it would put out, let's say, 0.7 out the red wire. At the same time, it would put 0.7 out the blue wire. That would turn on both the red and the blue guns, and we'd see magenta on the screen. If the computer wanted something to be magenta, but maybe just a little more red than blue, it might put out 0.7 out the yes, I'm just taking a moment to change the camera. Red. 0.7 out the red, thank you, and 0.5 out the blue, and it would still be some kind of a shade of magenta. It would just be a little more red than blue. If it wants something to be yellow, it puts out 0.7 out the red and the green at the same time, and it turns yellow. You get where I'm going with this. If the computer wants something to be white, it would put 0.71 out each of these three colors, red, green, and blue, and we'd see white on the screen. If the computer wanted something to be gray, let's say, there's white, let's say. The computer wants something to be gray. Well, gray is just dim white, isn't it? It's white, but it's dimmer. It might put out only 0.5 out red, green, and blue, and it would be gray on the screen. Let's say the computer wants something to be pink on the screen. Let's think about this for a second. If I put out 0.5 out of each of these, I have gray. If I put 0.7 out the red and 0.5 out of each of the other two, it's white or gray, but with a little more red than the other two colors, right? So it has to be pink, doesn't it? Some kind of pastel color. It would be the same for green or blue. If we want to make a kind of a light pastel green, we would put maybe 0.7 out the green and 0.5 out of the red and the blue. You get where I'm going with this. And of course, if all three of the colors are, if there's no voltage on any of these wires, then we see black on the screen. We have a name for these signals. These three color signals that come out of the board that go into the monitor are technically known as video. That's what video really is. Video ain't like MTV and like music videos. You know, to a technician, what video is video is the name of the signal that controls the electron guns. That's what video is. It's the name of the signal that controls the electron guns. The higher the video voltage, the more of that color appears on the screen. That's all there is to it. I mean, there's nothing mysterious about it whatsoever. Now, the video signal that comes from the computer board is not powerful enough to drive the electron guns in the the cathodes in the electron gun. And it's the cathodes themselves that we are controlling to turn the guns on and off. We control the voltage on the cathodes. But this voltage that comes out, and we'll take a great detailed look at that later on. But this voltage that comes out of the computer is no way it's powerful enough to drive this thing. We only have 0.7 of a volt coming out of the computer here, but the electron guns might require 175 volts to operate. And that really depends on the monitor. I've seen it as low as 123. I've seen it as high as 190. Ray, seen anything out of those range? How much? 80. As low as, you've seen it as low as 80. That's interesting. I haven't seen that. Maybe I just haven't looked, really, because it's not a failure item too often. But regardless of that, we can't hook it up directly. So that has to be amplified first. So in the monitor, there are 3 amplifiers here. And we use a triangle as a symbol for an amplifier. Whoops. We use a triangle as a symbol for an amplifier. Inputs on the left-hand side, outputs on the right-hand side. This is true of schematic diagrams in general, by the way. It's something that you should know about when you're looking at schematic diagrams. In general, in a properly drawn schematic, inputs are on the left-hand side of the schematic diagram, and outputs are on the right-hand side. And things move from left to right. Are there exceptions to the rule? Yes, there are. And as we go through this later on, I will show you some of these exceptions, and I'll show you where we have an output, but it comes off the left-hand side of something. Don't worry about it. But in general, inputs are on the left and outputs are on the right. So, for example, when we look at a schematic diagram for a monitor, what's the output? Well, the picture tube is the output, so you'll almost always find that on the right-hand side of the schematic. I can't think of a single exception offhand. And so inputs are on the left, outputs are on the right. So we have these 3 amplifiers here. Golly gee whiz, guess what we call these amplifiers? that take the video signal in and amplify it. Video amplifiers, yay! All right, so it's pretty logical, isn't it? So we have 3 video amplifiers here. 3 video amplifiers in the monitor. And these are identical video amplifiers. Really cool thing about the way monitors work. It is virtually impossible for you to fail to diagnose a color problem in a monitor because you have 3 identical but separate amplifiers. So, and when we go over this tomorrow or Thursday, whichever day we do it, you'll see how this works. It's impossible for you to fail to diagnose a color problem because you have 3 identical circuits, meaning that you can always compare one circuit to the other. And you'll see how this works when we start looking at the video amplifiers. You'll see how easy it is to diagnose color problems. I would say impossible for you to fail to fix it, except that you might have a bad picture tube, which you can't fix. But it's impossible for you to fail to diagnose it. I mean, it's just, video problems are the easiest of all the problems that you can work on in a monitor. Video problems are absolutely the easiest to deal with, the easiest to diagnose. It's just real simple because, again, you have these 3 identical amplifiers. Basically, video is really kind of the same thing as audio. Video and audio are kind of really the same thing. The only real difference between them really is the final output device. For example, in your home stereo, you have a CD player, for example. Well, you know you can't take the output of the CD player and run it right into your speakers. You have to go to an amplifier first. So there's a right channel amplifier, and here's the speaker. And here's a left channel amplifier. And here's the speaker. Now you'll notice in this case, I have 2 outputs, but I drew one on the left and one on the right. So the outputs are not always on the right-hand side. There's an exception. If I were to draw this, I suppose, more technically correct, I suppose I should really draw it like this, with one amplifier here, that's a speaker, and another amplifier here. Whoops, keep wanting to turn that into a diode. And another speaker like there, and label them left and right. But to me, that's more logical to put the left out here and the right out there. But 6 of one, half dozen of the other. So you'll definitely see exceptions to the rule. But the point that I'm making here is this: that you can't take the output of the CD and hook it right up into the speaker. You have to amplify it first. So you have an audio amplifier and then the speaker. Same thing here. The only real difference is the final output device. With audio, it's a speaker. With video, it's the CRT. But other than that, they're pretty much the same. With video, the higher the voltage, the brighter the color is on the screen. With audio, the higher the voltage, the louder the sound is. But other than that, they're really pretty much the same thing. Yes, the video works at a higher frequency. For those of you who are going, well, wait a minute, video is much faster. It's true that the video works at a higher frequency, but basically they're really the same thing. In order for the monitor to display a stable picture, like the one that you see here, somehow the monitor and the computer have to be synchronized with one another. In order for that thing to show a perfectly stable picture like that, somehow these 2 things have to be synchronized. S-Y-N-C-H-R-O-N-I-Z-E-D. Synchronized. Now, there is no feedback from the monitor back into the CPU itself. In other words, it is not like the monitor is saying to the computer, it is not, as the beam is going across here, it is not that the monitor is saying to the computer, okay, I'm over here now, please send me blue. Oh, I'm over here, I need some red. Oh, turn on red and blue at the same time. That isn't the way it works. It is the computer that tells the monitor what to do. The computer tells the monitor when to start and stop drawing each line of raster, which, by the way, is now known as a line of video, just FYI. When you have a picture on the screen, that line of raster we now refer to as a line of video because it has color in it now. somehow the computer has to talk to the monitor. And the way it does that is with two other signals called the synchronization signals, or sync for short, S-Y-N-C for short, synchronization or sync. I've seen it written S-Y-N-C-H, but that looks like cinch to me, and I think it should be sync. So S-Y-N-C. And there are actually two wires, or two different sync signals, that come out of the computer board that go into the monitor. One of these signals is known as vertical sync, and the other one is known as horizontal sync. And these are just two additional wires that come out of the computer board that go into the monitor. And those are the signals that keep the monitor synchronized so that it's doing the right thing at the right time. The easiest way for me to describe sync to you is to show you what it looks like when you don't have sync for some reason. Let's see if I can demonstrate that for you. Let's put it on a nice pattern here. That's a good enough pattern. Okay, I'm going to try to disable the sync. I didn't actually try this ahead of time. It should work. We'll find out. Oh, or not. Why would that go out with loss of vertical sync? Yeah, and then it goes out. There we go. All right. If for some reason you lose vertical sync, the picture will roll vertically like this. Now, if you happen to have a vertical hold control on the monitor, which I don't in this case, I might be able to slow this down. But you can see how this is rolling vertically, can't you? So, I mean, if you saw this on your home TV and you happen to have a vertical hold control, which most of them don't anymore, you would try adjusting the vertical hold. If you could get it to slow down but never stop, that would be loss of vertical sync. So when you think vertical sync, just think, is the picture rolling? The vertical sync prevents that from happening, is the easiest way to think of it, really. Horizontal sync is a bit weirder. When the monitor loses horizontal sync, it does something like this. And your big clue here is, do you see the scrambled up, jagged diagonalness of this? And in fact, if I put it on the color bars, you can really see it like that. Your big clue is here, and in fact, let me just kind of zoom in on this so you can kind of take a better look at it. Zoom. Let me just zoom in on this. My battery's dead. Oh, my batteries are dead. They are dead. Your big clue, oh, that's a nice picture right there. Do you see the jagged stair-step effect here? You can see how it's all jagged like that. That's really what you're looking at. And it can get smaller and more weird than that. That's actually rolling at the same time on the screen, but it's really not in real life. Right? So you see it doing weird stuff like that. That's when you have loss of horizontal sync, is when it has that. The big clue is that jagged stair-step kind of effect. And as soon as I re-enable the sync, it'll come back right in place. So that's the effect that you're looking at. What's really happening is that at the end of each line, the computer's sending out a sync pulse. On that horizontal sync pulse wire or on the vertical sync pulse, when the computer is done drawing one line of video, or when the computer is done drawing one entire field, it then sends out a momentary sync pulse. When the monitor receives that momentary sync pulse, it tells the monitor to turn the guns off, remember the blanking circuit, and then turn the guns off, and then quickly bring the beam back to the left-hand side. So at the end of every line, the computer sends out a horizontal sync pulse. The computer is telling the monitor to turn the guns on, okay, make it blue, make it red. You know, as the beam is moving from left to right, it's saying turn all the guns off. Now just the blue is on. Now just the red is on. Now red and blue are on because it's magenta. Now just the green is on. Now green and blue are on because it's cyan. Now yellow and red and green are on because it's yellow. Now all three are on. When it gets to the end of the line, the computer knows it's done drawing the line. It sends a signal out the horizontal sync wire. When the monitor receives that, essentially what it's doing is giving the monitor a little kick in the ass, and the monitor goes, "Rah! Okay, I'll retrace." And that initiates that blanking and retrace sequence, right? The blanking, it turns the guns off, and then it quickly scans back to the left. The beam literally flies back to the left-hand side. When the computer is done drawing an entire field, the computer knows the beam is down there. It says, look, I'm done drawing the field. Then it sends out a vertical sync pulse. When the monitor receives that vertical sync pulse, again, it initiates that blanking and retrace sequence that causes the beam to eventually make its way back up into the upper left-hand corner. Make sense? Not that you care about that. You don't care about that. All you care about is if I'm missing vertical sync, it'll roll vertically. If I'm missing horizontal sync, it'll do that jagged, freak-out, diagonal weirdness that you see. That's loss of horizontal sync. But I got to tell you, sync circuits are also extremely reliable. Ray, how often do you see sync failures? Oh, wait, and Chris, there's how much?
20%.
Really? On your particular monitor, brand, something or other that we won't talk about right now? That's interesting. Well, there are a couple of unique failures that we'll talk about in sync. Exactly. Well, don't worry about this. Pay no attention to the man behind the curtain. We'll cover all this in great detail later on. But the sync circuits in general don't work very hard, and in general, it's not the sync circuit itself that fails. It's the power that goes to the sync circuit. There is also a sync amplifier in here. In addition to the red, green, and blue amplifiers, there's another amplifier for the vertical sync and the horizontal sync. And then these sync signals then go to the deflection circuits, don't they? The sync talks to the deflection to tell it when to start moving the beam from left to right, when to start the beam from the top, going from the top to the bottom, et cetera, et cetera, et cetera. And again, we're going to talk about all